Good afternoon. So this lecture and the next lecture is about implementing pipeline systems, and for this we have to learn a few new concepts about concurrency, how to express concurrency in Bluespec. In fact, it's more a question of understanding it than learning any new syntax and things like that. So that's what this lecture is, and it's quite important. It's also quite different than what you will find in any textbook. All right, so implementing pipelining. So we have a synchronous pipeline. At every clock's edge, we want the data to move to the right, so we can be processing multiple things at the same time. In any pipeline system, there is a question of how you're feeding things in and out. So let's just have a simple model that we have FIFOs at the input and output. So I pick something from the FIFO and then I want to process it in several steps and put it out in the output FIFO. And input FIFO may not have input all the time in it. Sometimes it may be empty, so we have to deal with those cases as well. If you want to write it down as a rule of what's going on, I think it is quite straightforward that in this rule, which I'm calling synchronous pipeline, you dequeue the enqueue, right? And in S1, you store F0 of whatever input you got. In S2, you store whatever F1 of whatever input you had in S1. And then you take the output, whatever was in S2, and put it out in the output queue. Output queue, NQ is F2 of S2. So it seems, I think, pretty straightforward to write this. And the common refrain is, when can such a rule execute? What is the implicit guard of it? And by now, all of you should be experts in that input queue has to have an element, right? And output queue better not be full. Both those conditions have to be true, before this pipeline can move. Very good. Okay, so there is a slight problem in such simplistic designs. Actually, it's quite incomplete. Why is it incomplete? Consider the following situation. Suppose you have a token in this pipeline, a green token, right? And there is nothing in the input queue. So what will happen in such a situation? The rule will not fire, right? Because there is nothing in the input queue. And yet you can't leave this green token in the pipeline. It must move. It must get out somehow. So there is always an issue, and similar issue arises. So this is a question of moving this, whatever information you have in the pipeline out. You can call it the stopping condition. At the end of the day, you can't leave anything in the pipeline. And similar problem exists also at the input time. How do we get it going, in this pipeline? But there is also an issue of, if I'm not putting something in every time into this synchronous pipeline, then there are things which are gaps, things which are bubbles, things which are invalid inputs, right? I mean, there are invalid values in these registers. So somehow we have to mark this, right? We want to modify these rules to be able to deal with this missing information, missing values, because we did not put in something in the pipeline every time. And the general solution to this problem is you associate some valid bit, right? You say, oh, register contains something or it doesn't contain something, which I could have also encoded as a maybe type in this. So let me try that. So let me explicitly attach a bit to every register, every pipeline register. So S1 has this valid bit V1 and S2 register has valid bit V2 associated with it. If it's true, that means the register has something. If it's false, that means the register contains garbage. It's empty, it doesn't have anything in it. Okay. So before I try to write any Bluespec, let's do a little bit of analysis, right? So I'm giving you 4 conditions I'm looking at, whether input queue has something or not. So that condition is specified by not empty. That's what NE stands for, not empty. Similarly, output Q should not be full, so I'm calling it not full condition. And in the middle, what's happening to V1 and V2, I'm calling it V1, valid V1 and valid V2. So suppose I gave you this condition. What does the first row represent here? That's the best case, right? There is something in the input queue, every stage has something, the output queue is not full. As long as that is the case, what action do I perform? Does this make sense? In S1, I have copied from the input, applied function F0 to it. In S2, I have copied things from, whatever was in S1, applied function F1 to it, and so on, right? So all three actions are shown here. The last stage, I'm enqueuing something. Is everybody with me? Now, what is the answer for the second row? What should happen in that case?
You have to stall.
Sorry?
You have to stall.
Fantastic. It cannot move, right? Because output is full. So if output is full, then you can't put anything in it, right? Because it can't move. And if it can't move, then everything else behind it will get blocked. No action in this case. It's just going to stay there. Nothing is going to happen until somebody else pulls out something from the output queue. What about the third one? There is nothing in the input queue, right? But there is something in S1, and there is nothing in S2, and the output is still full. Fantastic, right? So what we can do is we can just move from S1 to S2 in that case, and you will mark V2 as true. Are these actions making sense, right? And I'm sure you can do this. You can write down all 16 possibilities here and write down the actions corresponding to it. And you are very good in writing case statements, so you could have written a Bluespec program or some program to accomplish this. But I think you'll have to agree with me that this is rather tedious. It'll be easy to make mistakes in this. And the idea seems so simple that I have a pipeline, I just want to keep moving things as long as there is something I've got in my hand and as long as there is space in front of me. After that, everything should happen automatically. Yes?
I'm confused why there's no action for the second line, but there is an action for the third line.
Okay, so you tell me. Analyze it.
Well, I think we had something that we wanted to move in the third line, but by the same logic, don't we also have something that we want to move in the second line? I thought the qualifier...
We do have something to move. The problem is the output is full.
But the output is also full in line 3.
But the V2 is not full. V2 doesn't want to move anything. V2 is empty. Right? So V2 doesn't have to move, but V1 can move into the place of V2, right? So it was internal movement, if you want. Hell will not break loose if you don't move it, right? You could have done no action also. But you can move it because sooner or later you have to compute it. So there are choices too. There is no unique answer. But the main point is, if you're designing a realistic pipeline, you have to worry about how it will start and how it will stop, right? And there is always extra work involved whenever you do that to a pipeline. So how about this? I think this is dramatically simpler to write. So let me replace those registers, stage registers, S1 and S2, by two FIFOs, right? FIFO 1 and FIFO 1 and FIFO 2. I think all of you will agree with me that this program is absolutely trivial to write. What is stage 1 rule? pick something from the input queue and put it in the next queue. What is stage 2 rule? Pick something from FIFO 1 and put it in FIFO 2. Yes? Are these rules easy to write? Yes. Good, good. All right. Let's ask our usual questions about this. So when can stage 1 rule fire? When there is something in and output is not full, right? When FIFO 1 is not full. Good. Now come some interesting questions. Question number 1. Can all these 3 rules fire concurrently? Can all these rules execute concurrently? Yes, why not? Yes, good, good, good. Right? But there is a caveat. Right? They interact through these FIFO 1 and FIFO 2. So if somebody is trying to enqueue in FIFO 1 and somebody else is trying to dequeue from FIFO 1, then your FIFO implementation has to be such that this enqueue and dequeue can be done concurrently. Because if you gave me a FIFO implementation, where these two FIFO in and out, in enqueue and dequeue cannot be done in parallel, cannot be done concurrently, then this pipeline is not going to quite function the way you expect it to. So for all 3 rules to go in parallel, it's essential that FIFO has some special properties, like it must support concurrent enqueue and concurrent dequeue. So part of today's lecture is to develop this vocabulary. How do I say this? How do I draw these distinctions? How do I capture these properties? Because this is not about functionality. This is about concurrency, right? What can be done in parallel and what can't be done in parallel. How about this situation? I'm just asking, can F1, stage 1 rule and stage 3 rule go on in stage 2 rule can go on in stage 3, whatever, rule go on in parallel? Yes, always, right? Because they don't interact with each other. There is no shared resource between the first rule and the third rule, right? This is putting in FIFO 1 and this is picking up from FIFO 2. So all these enqueues, dequeues are separate. So yes, this can definitely go on in parallel concurrently, regardless of what kind of FIFO you have. Now, why am I so hung up on this? I'm saying this is an easy way to write down this pipeline, right? Anybody can write these 3 rules. There is nothing to it. But if these 3 rules don't fire concurrently, then it's kind of a bogus pipeline, right? I mean, a real pipeline, everything moves, right, when it can. So if it cannot move, then you haven't quite finished your task. This is the first example you are seeing where you may get it functionally correct, but not correct in the sense of what motivated the whole hardware design for the pipeline system, which was to increase the throughput. Increased throughput means these rules must fire in parallel. Okay, so that's an essential quality of these things. So depending upon what you are doing, at times it will seem correctness is the biggest headache. The moment things are correct, then you say, man, performance is the real headache. Because if it doesn't run fast enough, what's the point? Right? I could have done much simpler things. I didn't have to go through all these FIFOs and this and that. I could have just stuck to a combinational circuit, which combined F0, F1 and F2 into one thing. So please understand that if we want to deal with concurrent systems, if we want to deal with high performance systems, we need some handle on this concurrency issue. Okay, so multi-rule systems, and you may say, I have already written so many multi-rule systems. You wrote lab 5, right? And you wrote the cache lab. All of them have lots of rules in them. But those labs are all very carefully designed in such a way so that at a given time only one rule was enabled. So if you had a control token, if you had a ball, right, and you had many rules, it was either here, here, there, here, etc., right? So you didn't have to worry about concurrency while writing those things because we deliberately designed those multi-cycle processors. We deliberately designed cache to be blocking so that there was no concurrency issue with it, right? You took some instruction, did this step, this step, this step, and got completed after that. But now we are interested in instruction pipelining and arithmetic pipelining. So we are going to be dealing with a new thing, which is multi-rule systems, where multiple rules may be ready to go. And you said, that sounds good. If multiple rules are ready to go, why not let them all go? Right? Well, problems. And that's what we want to understand. Right? So in multi-rule systems, consider a system where multiple rules are ready to go at the same time. And in such a system, the questions I would like to answer today are, when can two such rules be executed together? What does it mean to execute rules together? And I mean both in terms of some high-level concepts, right? And I also mean it in terms of hardware generated. How does the hardware look different? Whether these rules are firing concurrently or they are not firing concurrently. So both these questions are interesting, though the second one, you don't deal with it explicitly. It will be all done by the compiler for you. But when you are trying to debug your program for performance, it will say, man, it's taking twice as many cycles as it should have. That means some rules are not firing concurrently. Right? So at that point you need some at least vague understanding of how the hardware is generated from it, and I'd like to clarify some of that today. Okay, so first thing, when you have a multi-rule system, you have many rules that are enabled. Pick any one of them. Just one, right? Pick any rule and execute it. What does that mean? Compute the next state and then go and update the next state. Now you are back to step one again. Maybe multiple rules are enabled, pick one again, right? So this is a highly non-deterministic system. Amongst the enabled rules, you just keep picking one and executing it. Whenever a system has this property, it's called linearizable. That there are many actions taking place in your system, but ultimately, even if they happen concurrently, ultimately they can be understood as if one thing happened at a time. As if this rule happened, then this rule happened, then this rule happened. And it's an implementation detail whether they actually happened in parallel or not. Right? So this property, any legal behavior of a Bluespec program can be explained by observing the state updates obtained by applying one rule at a time. Concurrent execution just means that you took a jump. Instead of going from here to this state to that state, you're directly going to that state. Right? So instead of taking two steps, you may do it in one, because of concurrent execution. So this is called the semantics, one rule at a time semantics, or linearizability property of systems. And believe me, when you study concurrent systems in any course, right, because you will do that sooner or later in the systems courses, operating systems or algorithms courses, this is the sledgehammer. We always want to understand the behavior of systems in terms of some sequential actions, even though many things are happening in parallel in such systems. So this is some very important property of systems that we want to preserve. But for performance, and today's lecture is as much about performance, we want to execute many of these rules concurrently. Got it? Yes?
So is this linearizability just an analysis tool, or is this?
Well, I mean, yes, it's analysis in the sense that your system is producing right answers. If it's producing wrong answers, then it's a different thing. I mean, then it's then you have, how should I say this? We don't know right now what is right or wrong. We are saying, given a bunch of rules, only answers that are acceptable to me are the ones which can ultimately be produced by doing one rule at a time in some order. And if you produce an answer which is not consistent with that, it's said to violate one rule at a time semantics. Okay, concurrent execution of rules. So this is what I want to illustrate next. Two rules can execute concurrently if concurrent execution would not cause a double write error. Well, this we have been seeing from the beginning, right? Because the moment there's a possibility of double error, we treat it as an error. But this is the other condition. Whatever behavior we observe, the final state can be obtained by executing rules one at a time in some sequential order. And rather than so many words, let's look at some examples. All right. Here is a two-rule system for you. The first one is saying x gets x plus 1. The second one is saying y gets y plus 1. Can these two rules execute concurrently? Sure, right? I mean, they have nothing to do with each other, right? But I want to be a little bit pedantic about it. I want to analyze it, right? So let's analyze it a bit. Suppose the initial values of x and y is 0, 0, right? I want to consider 3 executions. Let's do them in parallel. Let's do them together. Is there any double write violation? No. And what does parallel execution mean? You always read the old values, right? I mean, whatever updates you have, you can't see them. So if initially it was 0, 0, what answer should you get here when you execute them concurrently? 1, 2, right? The second one says, suppose I execute RA first, rule A first, and then I do rule B. What answer will you get? The same, right? Suppose you do rule RB first and then you do rule RA. Again, you get the same answer. So what you see is that the concurrent execution is consistent with both orders, right? It's as if RA executed before RB, or it's as if RB executed before RA. Whenever you have such a wonderful situation, we call it conflict-free. This is the best possible situation, conflict-free. Surely you can execute these rules together. That means they don't interact with each other. Okay, let's consider this example. What is the difference in example 2? X depends upon y, and y depends upon x. What will happen if you executed these rules in parallel? You will read the old values of x and y, which is 0, 0, and what will be the new values of x and y? Everybody agrees with this? Now do RA first and then do RB. RA first and then RB. RA will produce 1, 2, and then RB, now that state is visible to RB. It will produce Is it clear to everyone? These answers? Why am I getting 1, 3 after doing rule RA? Or did I make a mistake? I do RA. Oh no, I'm doing both, right? I do RA and then RB. So after I do RA, I will get 0. Sorry, I'll get 1, 0. And when I put 1, 0 in the second one, I will get 3, and x doesn't change, so it remains 1 at that point. So that's why I got 1, 3. I should have probably written the intermediate steps here. Has everybody figured this out? Okay, so now the answer is written on the screen, right? The thing we got by executing concurrently certainly doesn't match if we do RA and then we do RB. It also doesn't match if we do RB first and then RA. And therefore these rules now, they should not be executed concurrently because either order doesn't match the concurrent execution. So we say such rules conflict. Here is a slightly variation of this example. Look at this example. What's happening here? X gets y plus 1, and y essentially, the second rule essentially ignores x. X gets y plus 2. Okay, so parallel execution is still the same. You'll get 1, 2. But now tell me what will happen after you do RA. What will be the value if you do RA only? And then what will happen when you do R1, RA followed by RB? One, two, right? We have a problem here, right? But this is a very interesting case. What that shows is if you executed them concurrently, it does not behave as if RA happened before RB. But it does behave as if, it behaves as if RA happened before RB, but not as if RB happened before RA. So this is a very interesting case. We say, yeah, you can do these rules together. You can fire these rules concurrently, and it behaves as if RA happened before RB. Right? So we use this syntax for that to indicate that RA happened before RB. Because our contract in one rule at a time semantics is only this much, that the final result must match some sequential order of execution. We don't say which one, right? And it matches this one. It matches the concurrent execution which produces 1, 2, matches the fact as if RA happened and then RB happened. Why is that the case? Because whatever RA does doesn't affect RB. It doesn't use X anywhere. So because it doesn't use X anywhere, it's not surprising that it behaves as if this happened and then this rule happened. But it's not true in the other direction. The first rule does use Y. So if you do this one first and then RA, you get different answers. Okay, good. So what compiler does for you is if you fed all these rules to it, you can ask for this information. It will tell you what conflicts with what. So for example, it produces something called a conflict matrix. So it says RA conflicts with RA. Obviously RA conflicts with RA because both are trying to update X. But what about RA and RB? In this example 1 it was conflict free, right? And these matrices are symmetric in a funny way, right? So C means rules can't be executed together, and CF means rules can be executed together. It's fine. Now what conflict matrix does it produce for the second one? Fantastic, all C's. And for the third one, RA happens before RB, and by symmetry you can say that means RB happens after RA. Right? So that's the conflict matrix. So you are not doing this. Bluespec compiler is doing it for you, right? So anytime you write rules, you can ask for conflict information. And it will show you, what rule conflicts with what. Okay, rules can be executed concurrently, the net effective as if RA executed before RB. Very good. Okay, so far what I have shown you is how rules execute in parallel, whether they can execute in parallel or not. We can ask the same question about the input methods of a module, interface methods of a module, right? So register is our most primitive module, in which we allow register reads and register writes. So two register writes conflict, that's what we have been saying, and two register reads are conflict free, you can read them in parallel. But if you do read and write at the same time, what effect do you see in a register? You will read the old value and then you will update it, right? That's like saying read comes before write. If you do RA and RB, if you do read and write into a register in parallel. So that's the most primitive conflict matrix you have. Everything in Bluespec is derived from this basic conflict matrix of a register. Two reads can be performed concurrently, two concurrent writes conflict and are not permitted, and a read and write can be performed concurrently, and it behaves as if read happened before the write. Yep.
So when Bluespec does when it makes the hardware for concurrent execution,
yep.
How does it encode the less?
So it's coming. Okay. Very good. That's where I'm going. Okay. So the most important thing here is conflict matrix for registers used systematically to derive the conflict matrix of all interfaces. That's the work Bluespec compiler is doing for you. It starts bottom up and it keeps applying this rule, and it can figure out the conflict between any two methods. But right now we're going to do without the Bluespec compiler. You're going to act as a Bluespec compiler. Remember our favorite example of one-element FIFO. Okay, so it's very easy to fill NQ and DQ conflict with themselves. Why? Double writes. Instantly obvious that you can't do a NQ or a DQ. What about first?
It's conflict free.
It should be conflict free, right? Because it's not affecting the state of the system. Both of them can read it. Now comes the interesting case. Let's analyze what is the relationship between NQ and DQ. So look at the code for NQ and DQ. Actually, even before I analyze, you realize something. NQ and DQ are mutually exclusive, right? One requires the condition V, the other one requires the condition V bar, right? So the question is absurd. Can you do them together? Well, they're never going to be enabled together, right? Because our high-level idea is that unless the ready signals are ready, you can't use a method. So since their ready signals can never be together, true together, they cannot be called together, ever. So I'll just note it down as mutually exclusive. So until now I had C and CF and less than or greater than, right? Now I'm introducing yet another symbol, mutually exclusive. Right? And by the same token, you will discover that first is conflict free with NQ. Mutually exclusive with NQ. Now you tell me the relationship between DQ and first. Can they be enabled together? Yes, they have the same condition, right? Do they ever update the same thing? First doesn't update anything, right? So there is no double write error. So if I do them in parallel, how will it behave? First happens before DQ. You pull something out and then you do the DQ, right? So this is the important thing, that if I do first and DQ together, right, you will first do the first part and then you will do the DQ in it. And anytime I make that kind of an entry, by symmetry, you can make the following entry. That first is less than DQ. Are you getting comfortable with this? Now, I started this lecture by showing you that elastic pipeline with FIFOs, right? Suppose I use this FIFO for my purposes of building that pipeline. What's the problem? This is totally inadequate, right? Because NQ and DQ can't even be enabled together. So there is no chance, if you use this FIFO, that pipeline is going to behave properly. Okay, so let's try another tag. Let's try two-element FIFO. Let's be generous. Let's not be so stingy that we're using one location. Let's use two locations in it. Okay, so initially both are, and I have a valid bit associated with them, so initially Q is empty. There's nothing in it. Now, when you do an NQ, you will store the data in DB and mark VB as present, as valid at that point. And whenever you do, and you can do an NQ as long as VB is false. That means it's empty, there is nothing there. You can put something in it. Okay, and DQ can be done as long as there is something, in the DA stage. Yes?
So if we have a two-element FIFO, that means that if it's initially empty, then the first thing we NQ will go to the first spot, and then the second thing will go to the second spot.
I haven't clarified that yet.
Right, because the description is saying you go you put the data in DA first and mark VA is true, but the
no DB first.
DB.
Oh, did I say first NQ will store the data in? Sorry, wrong. Typo. It should be a DB. Thanks. This is an important typo. That first NQ will store the data in DB and mark DB. I mean, that's consistent with the picture I've shown. Sorry about that. Okay. And let's further assume that if you have a two-element FIFO and there is only one entry in it, right? It will actually should be in DA and not in DB.
DA of the picture?
Yeah. Mm-hmm. So we always want to, in the steady state, we always want it to be on the right-hand side. Otherwise, my logic will be quite complicated. I get some input. Is there space? I'll have to check both the bits. No, I want to keep it very simple. Whenever I want to NQ, I only want to check this bit. Whenever I want to DQ, I only want to check this bit. And I will maintain this invariant that if there is only one entry, I always keep it in DA. Okay, good. We can write the code for this. Does this make sense? This time I think I got it right. Okay. So when you are NQing, you put it in DB and you mark VB true. What does DQ do? It just pulls out of VA, right? And just marks VA false, as long as VA had something. And first, same thing is true here. It returns VA, whatever is in VA. So what will happen? You start out with something empty. You do an NQ in it. Can you do a DQ after that? No, because DQ says something must be in DA, right? But it's still sitting in DB because that's where I NQ'd it. So I need some more bookkeeping rule. I need a rule which actually moves things from DB to DA, and that's this rule. So when there is something in VB, in this slot, and there is nothing in the next slot, then it's moving it internally. It's copying dB into dA. Are you with me on this? Yes?
So the intent of use for this two-element FIFO is still just with one element.
Yes, yes, yes. We are working very hard to make it conflict-free,
Okay.
right? And actually we have achieved that goal, if you see. Yeah.
Just add another stage in our pipeline for every FIFO that we have? Like, does it have,
Oh, if you had n-element FIFO.
yeah, like, does it take an extra number of cycles?
No, so I think if you wanted to design an n-element FIFO, it will take n plus 1 slots, not 2n slots. But let's understand this one first, because the thing I'm most interested in, what is the conflict properties of this? Do you agree that NQ and DQ now are conflict free? Can they be enabled at the same time? Is it possible that VB is empty and VA is full, right? That's possible, right? I mean, these are two independent variables, so that condition is possible. So that means that, and what action happens? Basically, if you just look at it blindly without understanding what the functionality is, there is no sharing of variables between NQ and DQ. NQ deals with this slot, DQ deals with this slot, right? So not surprisingly, it's all conflict free. Same thing is true with first. We are making progress. What that means is I can use this FIFO in my example I showed you earlier where I was trying to build a pipeline FIFO. Okay, now let's also add the canonicalization rule. What is the conflict of these methods with the canonicalization rule? It is not so cool, but you know, it is what it is, right? So you're seeing that it is mutually exclusive. How did I analyze it so fast? Can somebody tell me why is NQ mutually exclusive with canonicalize, that they cannot be enabled at the same time?
Look at the guard. You look at the guard.
If you look at the guards, it's obvious, right? Because NQ needs the guard VB to be false, right? And canonicalize needs the guard VB to be true. So clearly these two conflict, mutually exclusive, sorry. And similar analysis applies to DQ and first. So you can NQ and DQ simultaneously, but there is something in the black hole in the middle, right? You lose a cycle, there's a dead cycle. When you move, you arrange chairs again inside this FIFO, but outsiders can't tell. Outsiders are happy that they can use NQ and DQ together. Yep.
Okay, so we have like 3 different methods in Bluespec, I think, so far. There's action, action value, and value.
Yeah. Mm-hmm.
So is it true that for all non-value methods, so action and action value, we will have a conflict with
Always.
itself?
It's self-conflict, right?
Yeah. But then with value methods, it'll always be conflict-free.
Actually, I would like it to be true, but that's not true. Why can there be a conflict? Because suppose you were trying to read two things together in a register file. So if you had only one port, you can either supply address for the first read or the second read. So parameter-less read methods are conflict-free. If your read method has a parameter, then again there is a conflict. It's like a port conflict. You just can't use the port, right? Because there is already something else going on. But it's an easy fix. If you want, you can create a new port. Then you just go and create another read port inside. In fact, Bluespec compiler can almost do it automatically. Yes?
You said every valid Bluespec code can be generalized. So the example you gave before with x receives y plus 1 and y receives x plus 2.
Yes.
It cannot be written in Bluespec.
No, it can be written in Bluespec. It will just never execute them concurrently. It will execute them one by one. It's not an illegal program. I mean, we are asking a different question. We are asking the question, can these two rules execute concurrently? The answer is no. That doesn't mean they can't execute one at a time.
And which one does it exclude? And which one does it transfer?
Ooh, that's semantics say anything goes, right? It can pick any it wants, but in reality it will warn you. It will say, which one do you want me to go first, or something, you know. So there are many possibilities there.
But how do you implement this? How does it, I want this to be executed?
I think the implementation is, it'll warn you, but it picks the first thing in textual order. I will never rely on it. You know, because tomorrow another compiler writer may come and it may, you know, so these are the famous silent bugs in concurrent programs. But at least it issues a warning, you know, that there was a choice here. Okay. There are many other FIFO designs possible. How about this? Suppose I have a one element FIFO, right? And it's full, which normally means I can't enqueue into it, right? But suppose simultaneously somebody was dequeuing from it. At the same time somebody was dequeuing. It should be possible, right? Pull it out, put the next thing in, because that hardware is very good at that. You can do those kinds of things, right? Similarly, you can talk of another. So if you did this, by the way, you will get this sort of conflict matrix for it. You can do it together. It will behave as if DQ happened and then NQ happened. So this is known as a pipeline FIFO. And the other one, which is equally popular, is called a bypass FIFO. In the bypass FIFO, suppose the FIFO is empty right now. Right? It's empty, but somebody is enqueuing. So normally it's from an empty FIFO you can't dequeue. But it's okay to dequeue if somebody was enqueuing at the same time. That's like saying this value flew through the FIFO. Right? It just went straight out. Right? So this is a bypass FIFO, a very important hardware structure that is often used. It'll have a different conflict matrix. I don't expect you to study this. And how do we build such FIFOs requires yet a new addition to Bluespec. Actually, this is the only other addition, which is an EHR, and I will talk about it in L23. Right? So this is an extra thing that we'll do later on. But you can start using it. I mean, I can give you a pipe, you know, in the library you may find a pipeline FIFO and bypass FIFO, and you can use it because this will be the conflict matrix associated with it. Very quickly now I want to tell you about hardware generation. How is the hardware generation going to be affected? So let's look at concurrent rule execution. There are these two rules. By now you are all experts. You can generate this circuit for rule 1. Sounds good? But remember, there are those ready conditions, right? So since we are reading this, we are applying this method F, we have to worry about the ready condition for method F, right? It has to be conjoined with this, because if it's not ready, you can't use it. And you can do the same thing for the second one. And the simplest wiring of this would have been, right, connect this to this, right? You should be able to draw the circuit for it. That you can apply method F only if it's ready, right? So I'm taking the ready signal and joining it with it. Now this circuit is good. This circuit is correct. It will execute RA and RB concurrently. But what if you did analysis of your circuit, your module, and compiler came back and said, sorry, F and G conflict. If F and G conflict, what will happen to this? This will create enormous confusion. Now you have violated the golden rule here that if things conflict, you should not enable them at the same time, because then whole logic inside will go wrong. right? So this is not good. So this circuit is correct only if rule RA and RB do not conflict, which in turn implies that F and G methods of M do not conflict. So how do I know whether F and G conflict or not? That information is coming to me in the conflict matrix. I can just study it, I can look at it and say, do F and G conflict or not? This is a question independently answerable by how we wired this thing up. Suppose rules RA and B do conflict, then what circuit should I generate here? Because this circuit is clearly wrong in that case. Any ideas? Okay, since we don't have time, let me just quickly give you the answer. So we need a scheduler. So everything remains the same. It's just that what I'm going to do is guards of all the rules are fed to the scheduler. So you take these things and feed it to the scheduler. Right? And then using the conflict matrix, the scheduler lets only non-conflict rules proceed. So it will produce two wires that are connected to like this. In other words, the only thing in this whole design that depends on the conflict properties of various modules is the scheduler, which is also produced by the compiler. You don't write it, right? The compiler is producing the scheduler for you. So if it's conflicting, it will make sure only one of them goes. If they are conflict free, it will let both of them go. Right? So that's the idea behind the scheduler. It's a pure combinational circuit. It doesn't take too many gates. A correct but low performance scheduler, which you should be able to write very easily, is just a priority circuit. Right? Suppose I say both rules are enabled, but only one of them should go. So I said, okay, let the first one go. Can you write such a combinational circuit? Sure. I mean, you have two input lines coming out, but only one of them should be true. Okay, in a more complete picture, even if I have just one method being called from two places, I have to introduce a mux in that case. And it's essential that both the rules don't feed into it, because if both rules ever fed into it, it will be problematic because you're violating this thing. So we again control it through the scheduler. We feed the inputs, the enable conditions into the scheduler, and we take the output and put it over here. Again, if the scheduler is implemented correctly, it is guaranteed that only one of the inputs into this mux will be true. This is known as the so-called one-hot encoding. So one last piece of terminology, when you see this scheduler, right? So you have some guards going into it and some wires coming out of it. And in the Bluespec jargon, these things say can execute, right? Because all the rules that are true, right? These are the rules that can execute. But the actual rules that execute are the ones on which you get 1 on the output of those lines. So those things are known as will fire signals. Can fire, will fire. Yes, that's what the scheduler does. It disables something. All these rules could have gone, but by butting in, instead of directly connecting, you're connecting them through the scheduler. It makes sure that right things will happen. How? Because of the compiler help, I know the conflict matrix, therefore I can generate the scheduler. Again, the important thing to remember here is one rule at a time semantics, extremely important for arguments. This is how we will decide whether our design is correct or not, functionality. And then efficient hardware requires multiple rule execution, and therefore you will have to look at sometimes conflict matrix. Why are these rules not firing in parallel? And next time when I discuss the processor pipeline, we will do it step by step. We will see how to produce the answers correctly, and then sometimes we are going to be in for surprise that they don't fire concurrently. Right? Then how do I fix it? What do I do? All right, next time. And good luck with the quiz. That's tonight. No, Thursday night, not tonight.